So apologies for the slightly late start. It's partly to allow for a few people to arrive who are coming from the meeting at IMO. I'd like to just introduce the consortium, and then I'm going to shortly hand over to the first speaker, Dr. Corbett. The first slide here shows you the logos of the various organisations that were involved in the study, and it underestimates or undervalues the contributions of a large number of partners who, beyond those logos, were very generous with their time and with their data in helping us to put this piece of work together. It was a very short time period study. We were given the go-ahead to do the work about this time last year and had to have the study finalised by May in 2014. So we had sort of 5 months to do the bulk of the work, which left us very little time and was one of the reasons why we had so many partners involved. The other being that we were very keen to make sure we had good geographical coverage and weren't being too European-centric in our perspective on the shipping industry, and had the views of the various different regions of the world who have significant shipping constituencies represented within the consortium. So the logos, the larger logos you can see are the consortium members themselves, many of whom are very kindly represented today, but only a few of whom are going to be actually talking on the podium. And then the smaller logos are those partners who were very generous with their data and who gave us information about their ship's performance or satellite AIS data or shore-based AIS data that enabled us to do the study, which was extremely data intensive, as I hope you'll see in a second. So I'd like to thank and acknowledge the many partners who were involved in the work. The sequence for this evening is that we're going to give 3 separate presentations and run through the following topics. We'll start with a brief overview of IMO greenhouse gas studies in general. We'll then move on to international shipping's CO2 emissions over the period of the study, which was explicitly 2007 to 2012 for the historic study. We'll explain how we derived those emission estimates, and give some detail for the non-CO2 emissions that were also included in the study, SOx, NOx, etc. And then the final presentation given by Dr. Faber is going to outline the part of the work which looks at the future emissions, future trajectories of both CO2 and other emissions and how those are derived. So without further ado, I'm going to hand over to Dr. Corbett, who's going to start on those first 2 bullet points.
Thank you very much. Let me put this on. I think it's now on. Can everybody hear me? Okay? All right. Let me know if I start to get quiet. It will be a rare event, but I would like to know right away. What I'm showing here is essentially the results of the IMO greenhouse gas studies that have been done over the years. But I'm going to begin with an overview of how these studies got begun. The x-axis is from 1990 to 2012, and the y-axis is the million tons of CO2 that are emitted. The blue line represents the global total of all fossil fuel sources as reported by the IPCC Assessment Report 5. The red line is ships. And before I get into talking about how we estimated that red line, what I'd like to do is to point out a couple of blue dots that will arrive. In September 1997, there was a diplomatic conference in which the IMO was invited to study greenhouse gases from ships, and MEPC agreed to direct a study. And then there were 2 studies that followed on. One was in March 2000. It was for the year 1996. And the other was delivered in April 2009, and it was, its most recent year was 2007, but it also provided a time series back to 1990, thus the red line. And what we've presented this week is the third IMO greenhouse gas study, and it is delivered in 2014, but it goes through the dates 2012. And it covers that orange box area during which you can see what happened to global CO2 emissions. So let's talk a little bit more about that inventory. And in order to do that, you can perhaps begin to figure out that ships are a rather small percentage of the global total. In fact, across this period, they ranged between 2 and 3% of global CO2 emissions. And that sounds like a rather small number, but it is on the order of major nations. Here I show you the flags of the top 10 nations with their most recent years of CO2 emissions. And you can see that ships would be 6th in that list if they were counted as a nation, which they're counted separate from. So, for just to get a sense of that 2 to 3%, it is a rather important number with regard to the blue line. But in order to make that make more sense and talk a little bit about the trends, let me convert the raw numbers into an index where the year 2000 is equal to 100. So we lose a little bit understanding of the orders of magnitude, but we get very good visualization of the trends. And you'll see in these 4 lines, GDP data in this dark black line. And in the GDP data, you'll see the recession of 2009, in which GDP dropped by about 3%. And then you'll see in this blue line that same CO2 line from before. And in the gray line, you'll see what world seaborne trade looked like across the period 1990 to 2012. The CO2 number on the blue line dropped about 1.5% when GDP dropped 3%. And up until the second IMO greenhouse gas study, these were the results. The first study was a fuel-based study mainly, and it was able to do as good as the statistics would allow. And the second study was the first IMO attempt at an activity-based estimate. This study results show up here. You can't really see the light pink box, at least I can't, but you can see the brackets. From 2007 to 2012, the third IMO study presented the first year-on-year estimates for a period of 6 years. And you can see that the trend was flat or slightly downward, depending upon how your eye wants to draw that line. Now that's the results. They're rather, it's important to notice that there was some degree of decoupling both from world seaborne trade and from GDP, that because of the volatile behavior in the economy, high prices, a little bit of overcapacity, things we'll talk about later on. And that it persisted after the, let me just do this real quick. It persisted afterwards, even though the blue line recovers and the black line recovers right after the 2009 bottom. There's still some shaking out of behavior, et cetera, that we can observe in the period through 2012. The methods that we used, as I told you, is the first IMO study used a fuel-based method. It's what's called a top-down method in our report. And the second IMO study used a bottom-up method, at least insofar as the data allowed, which involved getting activity-based information or assumptions and then doing an analysis. And the third study advanced to those methods by a large amount by relying more and more on observable data, in many cases down to the beginning with observations at the vessel scale and then moving up. Now, the interesting difference between the top-down and bottom-up can be shown in these next 2 graphs. And this graph will summarize for you what's called the top-down estimates, the fuel-based summaries of statistics from the International Energy Agency. And the blue line represents the reported marine fuel statistics for all types of marine fuels that are reported. We performed the first analysis of uncertainty on those statistics that has ever been attempted. And what we found is that there are 2 key categories. There's uncertainty in many different areas, but 2 key ones that accounted for a large difference in the potential underestimate of fuel statistics versus the estimates when you look at the activity of the engines themselves. And the 2 were that on a world basis, the exports of the world should equal the imports of the world. Whatever gets exported somewhere should be imported somewhere else. And it turned out that they were not equal. There was an excess difference there that might be reallocated to shipping or perhaps other sources. And then secondly, transfers within the fuel supply system, say between stationary sources and mobile sources, etc., those were not net zero conserved either, which would suggest that if you're bringing in fuels for blending into a bunker operation, those transfers may be poorly accounted for, at least to some small degree, and that represents the very small bar at the very top. At the end of the day, it's possible that the upper bound of what the fuel statistics suggest is shown by those bars. So what you see here is a compilation. This will be, I'll walk through this slide 3 times. And what you'll see here is a compilation of, in the orange, the bottom-up activity-based Tier 3 methodologies and what we estimated the fuel consumption would be for each of the years that we studied in the third study. In 2007, our study could be directly compared with the 2009, the second IMO greenhouse gas study, and their activity-based estimates were within 3% of ours, albeit the uncertainty or the confidence on that number was much lower than it was on ours with the additional data that we were able to use to validate our values. The bottom up, the top down fuel sales statistics that I described to you without the uncertainty are in these green bars. And again, we could look at what the 2009 or second greenhouse gas study did relative to the third study. And we can see these green bars representing that additional uncertainty, potential uncertainty, up to an upper bound that we've estimated for this work. And what you can see is even where these numbers and these numbers are slightly different, the uncertainties overlap for all of the bottom-up and all of the top-down estimates, which gives us the ability to say that there's evidence that these methodologies are beginning to show some convergence, and the true factor is represented somewhere in the work that we've been done. And we'll talk more about how we have significant confidence in the methodologies and findings of the bottom-up results. I think at this point, I hand the microphone back. Thank you, sir.
Thanks. I should have mentioned at the beginning, the format is to start with these 3 presentations, but we're going to take any clarifying questions that people would want to raise after I've finished talking in a second, before we move on to the discussion about future scenarios. But then we'll have a more detailed discussion with wider questions after that. So, leading on from Dr. Corbett's slides, which outline the fact that there are these 2 different ways we can look at the total fuel consumption and the total CO2 emissions of the shipping industry. We can count all the fuel sold around the world, or we can look on an individual ship basis, try and estimate how much every ship's fuel consumption in the world was, and then sum those numbers. And it's that latter method that I want to talk about in a bit more detail. If we look at the fleet registries, IHS Fairplay, for example, there are about 60,000 ships that were active in 2007, and surprisingly that remained fairly constant over the next 6 years. So over the period of our study, we had to add up the fuel consumption of about 60,000 individual vessels over the course of their activity of a year. And to do that, we used a source of data which is called AIS. If I can just try and get this to play. So this slide in a second is an animation of just one type of ship, the VLCC tankers, the very large crude carrying tankers that move crude oil around the world. And each yellow dot represents an individual ship. In this fleet category, there are only about 500 ships. And you'll see their activity over the course of a month when I play it. Oh, let's try again. The comet tail behind the yellow dot gives you an indication of how fast the ship's moving. And you can see that there are quite a few ships which are actually stationary. So when we do these calculations, we can't just assume a certain pattern of behavior for individual ships. We need to look at them on an individual basis. And this data set has allowed us to do that for the first time with a reasonable degree of accuracy. So in 2011, with the benefit of the satellite observations of the ships, which gives you the detail in the deep ocean, we could see what ships were doing for a lot of the time and use that detailed information on a ship-by-ship basis to calculate fuel consumption. That source of data, unfortunately, wasn't available at the start year of the study, 2007. So I'm going to build through the data that we compiled, and we did that from a large number of suppliers and sources of AIS data, mixing data from shore-based stations, which are those base stations that were available in 2007. And here you have like a Coast Guard installation where there's a receiver on land, and that receiver typically has a range of about 50 nautical miles, which means that those receivers can give you a picture of shipping activity, but it's very much limited to areas where there's an interest in monitoring that, which in 2007 was not a global coverage, and it was certainly not covering the oceans. In 2008, there were more stations that we were able to obtain the data from, and that built in 2009 as well. But it wasn't until 2010, the first year that the satellites became available for collection of the data, that we start to see what ships are doing in the open ocean. And even over the period of the study in 2011 and then in 2012, we got even more data and even more detail about what individual ships were doing. So much so, to the extent that in 2012, we could see what an individual ship, an individual large tanker, bulker, container ship, for example, was doing on an hour-by-hour basis for 70% of the hours of the year. And for the remaining 30% of the hours of the year that we couldn't see what the ship was doing, we could make a very good estimate because we knew that it was only a few hours between when we last saw the ship and when we next picked up a signal of what it was doing. So we were able to build a very high accuracy picture of the changing speeds, the amount of time these individual ships were spending in port or at sea, at anchor, and from that information estimate both the fuel consumption and then the CO2 emissions. And I'll just run through the details of that method in this flowchart here. Apologies if you're towards the back of the room and the text is a bit small, but we can circulate these slides so you can look at this in more detail afterwards. So we have sources of AIS data from both shore-based stations, satellites, and in some cases multiple satellite providers. And we combined those different sources of information and merged them so that we made sure that there were no duplications of observations of the same ship from multiple different sources at the same time. That database of observations then had to be combined with fleet data. So within that satellite observation of the ship, we know its identity using its unique IMO number and can match that across to the fleet databases that give us the ship's deadweight, its length, beam, draft, installed main engine power, and many other parameters that we can use to describe the physics of the ship, its actual physical existence. And we merge those two data sets and apply some quality checks to say at what quality level are we observing that ship over the course of the year that we're interested in. For the ships that we can see with good quality coverage, we then undertake some estimates of their activity over the whole year and their fuel consumption for each of the periods of the time that we're observing them. And from that information, we then are able to build up a quality picture of a certain subset, a certain sample of a sector of the shipping fleet. So for example, a sector of those VLCCs we saw on that previous slide. We also had available to us, and I'll go into this in a bit more detail on the next slide, data from operators of ships. We assembled about 600 to 700 ships worth of data of noon reports from operators who are very generous with sharing their information on a ship-by-ship basis, which we could then match to those modelled estimates of fuel consumption. And that enabled us to carry out a verification that our computer model generated estimate of fuel consumption actually represented what the operators were measuring themselves on board that ship in terms of fuel consumption. So we combined that data set and then imputed what we couldn't see because of poor quality AIS data or missing observations of ships where we couldn't match them with the fleet database. And finally, in the calculation, we then produced the sum for subsectors of the shipping fleets and calculated statistics for the sectors. So I mentioned just a second ago the fact that we were comparing our modelled AIS-derived estimate of fuel consumption against operator data. This slide shows that comparison. And just to walk through it, we have the same units on the x-axis and the y-axis, but the x-axis is reporting the operator-reported fuel consumption, the value of fuel consumed that we obtain by summing fuel consumed and noon report data. Noon reports are reports made on board ships at approximately noon every single day and used to estimate how it's changing over time and what its activity is. So that's a type of data that is measuring the fuel consumption on board the ship. On the y-axis, we have the estimates coming from our AIS-derived model. And if every single ship observation, which is represented by individual crosses on this slide, was exactly identical between our model and the noon reported value, then we would see all of those values falling onto the red line, which represents the equal axis line. In this instance, what we observed was the black line. This is in 2012, so a year when we had very good AIS coverage. And you can see, according to the different colours, how well the agreement varies between different sectors of the fleet. So the red crosses up here represent some of the large container ships. The purple crosses here are LNG carriers. Yellow crosses are oil tankers. Blue crosses are liquefied gas blue crosses are bulk carriers, etc. And so we could investigate whether there was a ship type that we had our assumptions or our model particularly incorrect for. And broadly speaking, we were very reassured by this plot when we first produced it that we didn't need to revisit any of our fundamental assumptions, that they were giving us a good enough agreement to reassure us that the model was credible. The fleet that it is very difficult to do is the Lng Tanker Fleet. That's this purple cross here. And those familiar with that ship type will know that they often consume their cargo as fuel. So these are ships carrying around liquefied natural gas, which does happen to boil off during the course of the voyage. And that boil off is then sometimes used in engines as a propulsion fuel, which makes the collection of data in terms of that ship's fuel consumption quite difficult, and it makes the modelling of their fuel consumption even more difficult. So we think that we've got a legitimate excuse for not having such a good agreement on that particular ship type, but their significance in overall CO2 emission is relatively low, which is another good excuse as well. So looking now on a ship-by-ship basis, and again, apologies to those at the back of the room who might find that font quite hard to read, we can break down, and this is the enormous benefit of having AIS data rather than fuel sales statistics, which do not discriminate between fuel sold to an oil tanker versus fuel sold to a bulker. You can't decompose or disaggregate the data at all. But from the AIS data and the fact we know the IMO number of the ship, we can build the statistics of how much each sector of the shipping industry consumes and identify which sectors have more responsibility than others. And it's very clear from this slide that there are 3 sectors that dominate fuel consumption, and this is 2012 data again. So this is the container sector here, the longest graph, the bulk carrier sector and the oil tanker sector, which understandably have a larger contribution to fuel consumed and therefore CO2 emissions. Associated with this graph, you can also make out the different areas of consumption on board the ship. So the blue represents fuel consumed in the main engine. Red, which is used primarily for propulsion. Red represents fuel consumed in the auxiliary engine, which is used to power hotel services and machinery. And green represents fuel consumed in boilers used to generate steam for services on board. So shown here in 2012, we can see even in a year which observed a large amount of slow steaming, the main engine is still the very much dominant source of fuel consumption and CO2 emissions on board ships. This next slide shows year-on-year results. So that previous slide was the 2012 data only. Here we pick out the international shipping categories only and show the trends year-on-year of fuel consumption. So if we take the container sector here, 2007 is the darkest blue line, leading to 2012, the lightest blue line. And you can make out in the container sector that there's no particularly significant trend occurring over the period of the study. That's contrasted, for example, with cruise shipping. So the cruise ship sector from 2007 to 12 saw a steady growth over the period of the study, as did the liquefied natural gas sector here, which again is going to be significant when we look at some further results in the middle in a second. Oil tankers showed a decline, quite a significant decline. So there's a variation from one ship type to another in terms of the trend, which decomposes even further the data that Dr. Corbett just showed us about the aggregate whole shipping industry trend, which was a slight decline over the period. When we look on a ship-by-ship or a ship sector-by-ship sector basis, we see that there are some differences between the sectors. This next slide shows a little bit about the amount of variability there is within each of these sectors. So in this slide here, we're plotting the total consumption of fuel across the entire shipping sector for the sectors shown, so total consumed by containers. This now shows us the variability from one container to the next. And we're only plotting on this diagram here the main engine fuel consumption, so the fuel consumed for propulsion purposes. And the box and whisker here gives you some impression of the difference from one ship to the next. So the red line represents the median value of fuel consumed. So the median fuel consumed in the container shipping sector in this particular size bin, which is the largest container ships, that was about 34,000 tons of fuel per year for the median ship. But we can see that there's a range of values. This box outlines the interquartile range. So this is the 25th percentile ship, if you like, which consumed about 22,000 tons of fuel. And this ship here, which is the 75th percentile ship, consumed about 37,000 tons per year. And the significance of that is simply to say that this data gives us insight into the variability of the fleet, but also shows how it's very difficult to treat the shipping industry as a homogeneous sector. The individual ships can vary in their performance quite a lot, even when we just categorize ships within a given size category. So these are ships which carry a very similar amount of cargo, and within that sector we saw a variation in the interquartile range of between 24,000 and 37,000 tons of fuel, which represents an interesting variability, which raises questions: why are some ships consuming so much more than others? And that's one that this data is very useful for unpacking and going into. So I now want to just draw some conclusions about some trends in the sector in an example sector over the period that we studied. And here I'm just going to use the dry bulk sector as an example. These two plots show how between the period of 2007, which is on the left, and 2012, there was a growth in both the total fleet capacity and deadweight, if we sum the deadweight of all the ships within the sector, but also the average deadweight, so the average size of the ships within the dry bulk fleet. So this is all the dry bulk ships from the smallest to the very largest cape sizes in terms of average deadweight, but also total deadweight, which is the blue line. And these are all values indexed back to 2007. So 2007 is 1, and over the total deadweight, we saw an approximately 80% increase in the total deadweight capacity of this sector of the shipping industry over the period of the study. The next two trend lines, again indexed to their 2007 values, show us the total demand ton miles, which saw in the green line an increase over the period that we were interested in. And in this instance, there was an increase of about 20% of dry bulk transport demand between 2007 and 2012. And the important information there is that that increase in demand is significantly less than the increase in capacity in this sector. And what that reveals is the well-known phenomenon of overcapacity, and the fact that there are many more deadweight tons of supply in that sector than there are deadweight tons demanded, which is having a very significant impact both on prices but also on speeds, because the fact that we have low freight rates and high fuel prices means that these ships can, with good attention to economics, reduce their speed and still operate competitively within the marketplace. The consequence of that slowing speed is that despite the fact that we're increasing both the average size of the ships and the total number of ships, we saw the CO2 emissions within the dry bulk sector actually slightly decline over the period of the study. And that reveals itself if we look at the carbon intensity of this sector, which is the turquoise line, as a slight improvement in the carbon intensity, which in this case is showing a reduction. So the carbon intensity was high in 2007 and reduced in 2012. And by carbon intensity, I'm referring to the grams of CO2 per ton nautical mile of work supplied by these fleets in doing useful transport work, moving iron ore, coal, etc. around the world. And that increase in performance, in efficiency, if you like, was coming about both because the average size of the ships was increasing, and therefore there was an economy of scale associated with that, but also because of this slow steaming phenomenon, which enables the ships to operate with a higher efficiency than if they were going at their higher design speeds. The flip side of that trend, the fact that we've increased the energy efficiency of that fleet over the last 6 years, is that the growing capacity has this very much increased total installed power. And historically, over the period of similar to the periods that Dr. Corbett showed in his slides, if we look back to 1990, you can see a very close correlation between the installed power and the total emissions of the shipping industry. It's a good proxy for the total emissions potential. So the fact that we have this large increase in installed power within the dry bulk sector shows us that there's a latent potential for this sector to increase its emissions if utilization was to increase, if speeds were to increase, and productivity were increase if the market changes. And that presents a risk that we have a good news story at the moment, but a story that could change quite dramatically if the market changes and behavior changes within the sector. So to just finish with this dive into the bottom-up studies results, I want to end on this particular note of slow steaming. And this graph shows a contrast between what was happening in 2007 and what we believe was happening in 2012. And I'll talk through the components of this slide. So I've taken 3 example sectors of the shipping fleet, if you like, the world fleet of that 60,000 ships. I've got the average 5,000 to 8,000 TEU capacity container ship in these bars, the average 6,000 to 100,000 deadweight ton capacity bulker in these bars, and the average 80,000 to 120,000 ton capacity tanker in those bars. So that's approximately the Aframax fleet. And this is what their ratio of operating speed to design speeds were in 2007, the blue bars for each of those 3 sectors. And here we have that same ratio calculated in 2012. The green bars show that ship's average percent MCR of the main engine. So that's the main engine's power output in order to achieve the operating speed that we see in the respective years. So if you had a 10 megawatt engine installed in 2007, it would have been producing approximately, if it was a bulk carrier, it would have been producing approximately 7.9 megawatts of output power. It would have been set at that level of power output on average in 2007. Whereas that same 10 megawatt engine in 2012 was producing approximately 6 megawatts of power output. And that was brought about because of the change in speed, the change in speed. So this demonstrates one of the important characteristics of ships, the fact that if you reduce their speed by a small amount, you get a much more significant amount of fuel or power output consumption required from the engine. So 20% in this instance, we're just focusing on the containers example in these charts, a 20% reduction in the operating speed relative to design speed over the period resulted in a 50% reduction in the power output required from the main engine. And that very broadly translates through to similar changes in the total fuel consumed per day of operation. So the red charts here plotted on top of that data is the average daily ton per day value for each of those sectors and how they've changed between 2007 and 2012. And we can take 2 examples of that. One is the container sector. So the average 5,000 to 8,000 TEU containers were doing a 50% reduction in their daily fuel consumption over that period of the study. And we can contrast that with the tankers, which made a smaller reduction. And there are many different reasons as to why these sectors are different, but it again reinforces the importance of not generalizing when we look at the shipping industry, but taking sectors or even subsectors into detailed consideration to see if we can understand why they've changed. So that concludes the presentation on the inventory work that is within the IMO study. We can take a short pause at this point if there are any questions or clarifications before we move on to Dr. Faber's presentation, which is going to be on future emission scenarios, if there are any, or we can move straight on. Does anyone have any clarification questions at this stage?
Just anecdotally, do you have any idea what happened to container freight rates during the period when their fuel costs
I know they went down. I don't know how much they went down by. There might be someone in the room who can help me.
I know that they
Mark.
The rates declined chasing cargo until 2011, when they still weren't able to get cargo, but there were news reports that they couldn't reduce the rates anymore and cover the costs, and they kind of hovered there.
Is that tally?
The risk went down to non-economic, to levels where it's not economical to operate ships, so ships went to lay, particularly like sort of 5,000 Panamax sizes. They were very unattractive to use, wrong sizes, fuel consumption.
The fleet was underwater.
Sorry?
The fleet was underwater.
Thanks. Are there any other clarifying questions at this stage?
Sorry?
You
Yeah.
And economies of scale. And also any other indication of what about technologies or other measures by shipowners or fleet governments and regulation had, like the SAP, for example, had on this reduction, what was the effect?
So the study period is 2007 to 2012, and SEMP and EEDI come in 2013. So we're fortunately outside of that period. But you do raise an important point, which is that there could well have been technological interventions that were happening to the fleet that we don't have explicit data on in the way we've modelled it. However, if a ship had fitted a better propeller or a better rudder, and that had resulted in a lower installed power, that would have been picked up in the study. So we were observing a change in the installed power over time, some of which has to do with trends in changes in design speed, but some of which will be to do with changes in ship design itself over that period. That tended to be a much smaller change, from what we can tell, than the impact of operating speed change and activity in terms of days at sea. And we're in the process of trying to unpack that a bit further at the moment, but it's difficult on a ship-by-ship basis to get that information about exactly what their technical specification is, because that doesn't typically tend to be in the IHS Fairplay database.
And I can just add very briefly one quick example, again small in terms of total CO2 impact on the emissions, but we observed an increase in the natural gas-powered fleets. I think it was a 60% increase. It's a very small number, okay, so a 60% increase in a very small number is still a very small number. But there was an increase in the natural gas fleet, and we were able to see that technology enter into the fleet during those periods year on year. Interestingly enough, in the top-down inventories that I briefly talked about, even today, if you look at the fuel sales statistics, ever since the 1970s, there have been 0 natural gas sold to the marine sector in the statistics. But we know, especially by looking at the vessels, that there are vessels that purchase and use natural gas.
There are no other clarifications. We'll have more discussion at the end, so we can revisit some of this. I've just realised that I hadn't actually finished my slides. I got to the end of the bit which was about CO2, and I thought that was the end of my bit, but I've just got 3 slides left on non-CO2, which is the other emissions. So the study quantifies not just CO2, but also other greenhouse gas emissions, which include N2O, CH4, methane, and hydrofluorocarbons that we don't have on this table here, and then other pollutants, air pollutants, which are important to shipping, particularly SOx, NOx, and PM, particulate matter, which are obviously interesting because of their importance in MARPOL Annex 6, the regulations about SOx and NOx emissions. So we were also asked, as well as quantifying CO2, to quantify those emissions, and we did those both using the fuel consumption statistics and emission factors for fuels on a fuel-based level, and using emission factors that we embedded in our activity model, observing individual ships. And the graphs I've got next will show that. This slide is simply to illustrate that in order to conduct the work, we had to come up with a set of emission factors for the engines and fuels which are currently being operated within the fleet. And we carried that out by doing a rigorous literature survey of all the studies that were in existence at the point that we were carrying out our work, and combined what we thought was a consortium's consensus estimate of the best data that was out there for emission factors. That's a whole subject in itself, and one I'm not going to dwell on, but if you wanted to follow the references and how we did that, it's all in the third greenhouse gas study itself. So I just want to build on that comment that Dr. Corbett was just making about the significance in the LNG tanker fleet in particular, which has shown an increase. And I've given the message away here, but here we're plotting the trend of 3 of the key greenhouse gases, CO2 in blue, CH4, methane in red, and N2O in green. And if I just start with N2O and CO2, those two track each other very closely because they tend to be related to the same drivers. And they're not varying particularly depending on fuel and engine specification. But over the period of study 2007, on the left-hand side here, again indexed to the 2007 value at 1, over the period of study to 2012, we saw a 70% increase in the methane emissions from the fleet, which is significant at a time when CO2 emissions were remaining steady. And that increase is a lot to do with the fact that we saw an increase in the size of the LNG tanker fleet. And those are ships which are often consuming CH4 methane in their engines, particularly when it's a boil-off gas from their tanks. And associated with that, we have some degree of methane slip. So some of that methane goes through the engine, isn't combusted, and comes out of the exhaust. And as a result, creates an emission of CH4 of methane. And that's one of the key things that we're observing in this chart here. Now, methane is an important emission, and in the study itself we calculated the CO2 equivalent, taking into account the global warming potential of the CH4 and the N2O emission. And actually, even though we see that dramatic increase in terms of CO2 equivalent greenhouse gas warming potentials, that methane emission is still not significant relative to the very important CO2 emission. But it's an interesting trend, and Dr. Faber might mention that in his next slides too. And this final slide is on the summary of the results for the other pollutants, particularly SOx in orange and NOx in purple, shown here contrasted against the trend in CO2. And there are a couple of things to point out here. One is, it's interesting that SOx and NOx emissions have not tracked CO2 again. They diverge slightly, not dramatically. So whilst both show that over the period that we studied there was a slight decline, the SOx emissions during some of that period were actually higher. And that has a lot to do with the average sulfur content in the fuels sold around the world, which actually peaked in, I think, was it 2010 or 2011? So the average fuel content in 2007 of the fuel sold was lower than the average sulfur content in those later years, causing that increase. The other thing that happens, of course, is that the ECAs, the emission control areas, start to kick in with the 1% fuel limits towards the end of the study in 2012, and that has an impact on the fuel sulfur content that's being consumed within the sector. So there's an interesting trend on SOx. NOx shows a slight decline, and there are a couple of things happening there. One is to do with the lower engine speeds, the lower percent MCRs, which have a slightly different NOx emission factor, and the other is to do with the phasing in of the Tier 2 NOx engines, which is starting to have a consequence on the NOx emissions of the fleet overall over the period that we studied. So that genuinely does conclude the slides that I had to share, and at this point I'll pass to Dr. Faber and give you the microphone.
Thank you. Tristan, Dr. Smith and Dr. Corbett have talked about the emissions in the 5-6 years that the 6 historical years that were studied. Our terms of reference were also to make projections for future emissions. And that's the part of the work that I led and that I will present something on here. The Second IMO Greenhouse Gas Study also had emission projections in it, and you're probably familiar with this graph here that's often been reproduced and was taken from the Second IMO Greenhouse Gas Study, so the one that was published in 2009. And which showed a very rapid increase in greenhouse gas emissions in the period between 2007, which was the last historic year in that study, and 2050, the end year towards which the study looked. Now, since the publication of the Second IMO Greenhouse Gas Study, several important things have happened, which together formed a reason to update the projections. First, and probably most important, is that the IPCC, the Intergovernmental Panel on Climate Change, produced a new set of long-term socio-economic scenarios. And in fact, they didn't, as in the previously, they didn't only look at long-term socio-economic scenarios, but considering that climate change is also an energy transition, and we're looking towards an energy transition. They also have made very different energy scenarios, which are relevant to our study, as I'll show in a minute. A second development is that larger and more efficient container ships have entered the market. And as you've seen in previous slides, container ships really make up a very significant part of total emissions. And the extremely large and very efficient container ships that have entered the market since 2007 have a discernible impact on overall emissions. And a third reason is that since the publication of the Second IMO Greenhouse Gas Study, new emission projection methods have been developed that have two distinct characteristics from the previous one, which were mainly based on a coupling of transport work to GDP. Or tons of seaborne trade cargo on to GDP. First of all, is that methods have been developed that take transport work, so ton miles, as a basis for projecting emissions rather than tons of cargo. And the second is that they take into account potential non-linear relations between activity drivers, such as GDP or demand for fuel and coal, and activity. So allowing for example, saturation of demand over time. And for all these reasons, the Third IMO Greenhouse Gas Study has made these new projections. The model we've used for making these projections is shown in this graph, which I have developed for the study, but is actually every time I have to explain it, it becomes more clear that it's upside down, because when you read it, you have to start here. I'll go very briefly over the factors that we took into account when going from data or projections of GDP and coal and oil to emissions up there, and then in the next few slides dwell on some of the most important factors and how we have estimated them. So what we started with was a statistical analysis of over 40 years of data of transport work, maritime transport work, disaggregated into liquid bulk, dry bulk, and other cargo, so mainly unitized cargo, container ships and general cargo, and relevant parameters such as total world coal consumption, total world oil consumption, and GDP. And we found that in general there was quite a good fit between coal consumption and coal transport work. So it means that the average haul over which the coal was transported was constant over time. And also, for example, between unitized cargo and GDP. Then taking the GDP projections and the coal and oil consumption projections from the new IPCC scenarios, we could project transport demand. We equated that to transport work. This is of course, we know and we have seen in Dr. Smith's slide that transport demand and transport work doesn't always equate. There was an overcapacity of ships in the long term, but since as we're looking to 2050, we think that overcapacity over time will phase out. Transport work combined with assumptions on ship size and fleet productivity allowed us to calculate or project the fleet composition over time. So the number of fleets or ships in each type and each size category. We looked at speed, which is a major component in the energy efficiency of ships. Also into non-speed autonomous efficiency improvements. For that we used a combination of fuel prices and a marginal abatement cost curve of shipping, and regulatory efficiency improvements such as the EEDI and the SEMP that have already been alluded to. Now this together allowed us to project energy demand of maritime transport, disaggregated into ship types. We made assumptions on the fuel mix which will be used to meet this energy demand, looking at the energy content of different fuels and regulation on SOx and NOx emissions in emission control areas around the world, and then had fuel consumption per ship type, per type of fuel. We applied emission factors for CO2. Of course, that's very straightforward. For non-CO2 emissions, it was more complicated, and even more so that we found out this week that there is a mistake in the report in that respect, and could project emissions like that. So in the next few slides I will dwell on some of the most important factors and how we arrived at our assumptions for them. But first, some background on the general methods. We produced 4 scenarios on transport demand. The IPCC scenarios, as I told you, they have 5 socio-economic scenarios and 3 or 4 energy transition scenarios. I don't know exactly. We combined them in a way that was logical, had some internal logic, into 4 overall scenarios which allowed us to project transport demand. We had 2 scenarios on emission control areas, so control of SOx and NOx. One where the current emission control areas, which are in the North Sea, the Baltic, and around the US coast, would remain, but no other emission control areas would be adopted, and one in which the share of fuel within the emission control area would double over time. And this is also relevant because one of the methods to comply with emission control requirements in emission control areas is to use LNG as a fuel, which burns much cleaner, has no SOx and lower NOx emissions than heavy fuel oil, and so it has a relevant impact on the fuel mix. Hence the ECA/fuel mix scenarios. And we had 2 scenarios on ship efficiency. One where we assumed that the current regulation on ship efficiency, the EEDI and the SEMP, would remain in place over time, but the stringencies would not be increased, and also there would not be any additional market driven efficiency improvements. And one where we assumed that either through regulation or through market driven action, the ship energy efficiency would improve over time. We have assumed in our study that transport distances will remain the same over time. Now you might think that this is quite a heroic assumption. In fact, we had, as I told you, 40 years of transport data. Now, if you think back, or slightly more than 40 years, going back to 1970, if you think back about this period and what happened, the emergence of Taiwan, Korea, Japan, and later on China as locations for production, huge shifts in transport that implied. Over these times, we analyzed the relation between transport work in ton miles and total transport in tons, and it remained fairly constant. So even with these big shifts in where consumption and production takes place, the average haul is relatively stable, which in our view was a good basis for this assumption. And we did a sensitivity analysis of fleet production. The projection of transport demand builds on the IPCC representative concentration pathways. That's the energy transition scenarios of the IPCC for oil and coal. So in ship type words for tankers and dry bulk carriers, a share of the dry bulk carriers, and the shared socio-economic pathways for the other commodities, so container ships, general cargo ships, and the non-coal transport part of bulk carriers. Due to historical, the rest of the, and it projects year-on-year changes in demand up to 2050. Now, this is what the RCP scenarios look like. So the representative concentration pathways. Here you see historic demand for oil and coal up to 2012, and then you have one scenario in which coal and oil goes down quite a bit. That's the scenario that has a fair chance of limiting the global average temperature increase to 2 degrees, which of course requires a big shift and a big reduction in fossil fuel consumption. And at the top end, the 6 to 8 degrees temperature increase scenarios would see a continued increase in fossil fuel demand. This shows the world consumption. If I would plot transport work, it would look almost the same as this. This is based on the socio-economic scenarios, where we plotted a unitized cargo and non-coal dry bulk using the GDP projections from the shared socio-economic pathways as a driver. And one thing, if you look at these two graphs, that is immediately striking, is that the rate of increase of unitized cargo, but also of non-coal dry bulk, is much higher than of coal and oil. And one of the reasons is that in our statistical analysis, which allowed for some saturation, we see some saturation of the non-coal dry bulk, which is, for example, ore or wheat, maize, things like that, which kind of makes sense because, you know, for every additional pound you earn, you may not spend the same amount of money on wheat or products. This is the unitized cargo, which grows much faster. And combined, this shows the ton miles over time, projected from 2012 up to 2050. And as you can see from these two graphs, the unitized and non-coal dry bulk dominates all the other factors, even though now, and I don't know the figures by head, but I would say that tankers and coal dry bulk account for probably 30–40% of emissions or something like that. But over time, that share will decrease significantly, and container ships, the share of container ships will increase significantly. Few things we had to tackle, assumptions we had to make. First, on fleet size, what we generally did on all the major assumptions that we had to do, we conducted a literature review. We shared our interpretation of the literature with stakeholders. The International Chamber of Shipping, World Shipping Council, and other shipping organizations were very helpful in that respect, and really took time to comment on our papers. With regards to fleet size, we take into account developments in fleet productivity, as Tristan has shown you in this line graph. Currently, the deadweight tonnage of the fleet compared to the ton miles it produces is at an historic high or low, I don't know. There's an overcapacity of ships. We took into account that it will revert back in 20 years to the long-term average, so that some of the additional demand that you've seen in the previous slide will not lead to more ships, also not to somewhat to ships sailing faster, but certainly to ships filling up to a higher degree. I've lost my line. We take into account developments in fleet productivity and ship size developments, map cargo to ship types, so oil to tanker, unitized to container, etc., and calculate the year-on-year changes in the number of ships per ship category. Projection of ship energy demand. We start with the energy consumptions of ship in 2012, which was a result of the inventory study. Take into account regulatory efficiency improvements, again, where we conducted a literature review and consulted stakeholders on that, and autonomous efficiency improvements based on a MAC curve that was submitted by IMRS to MEPC, with the MAC curve had speed reduction as one of the measures and projected fuel prices. And then we have had two scenarios for the autonomous efficiency improvements. One with which was called business as usual, which has the current policies, policies that are currently in place, and modest improvements after 2030, and one with further stringency or additional policies or increased market-driven efficiency improvements. And the fuel mix, we have two fuel mixes. In both fuel mixes, LNG goes up over time, but in one fuel mix has a very modest share of LNG by 2050 of 8%, and the other has a more higher, I think it's 25% fuel mix, LNG share in the fuel mix over time. And then when we had the fuel mix, we applied the emissions factor to yield emissions. Now, this slide shows the CO2 results of our work. You see 4 bold lines and a number of thinner lines. The bold lines represent what we call the business as usual scenario, so it's basically the current policies and nothing else. And they show that depending on the socio-economic and energy transition scenario that you imagine, emissions will increase by 50% in 2050, so from 800 to approximately 1200 megatons of CO2, up to in a more when there's more economic growth and not so much climate policy, up to a growth of 250% in 2050. If you compare this to the second IMO greenhouse gas study, our growth rates are somewhat lower. I think the second IMO greenhouse gas study had at its highest a 300 or 350% increase, and also the lowest was somewhat higher than the current lowest. The other lines are the different ECA/fuel mix scenarios or the different efficiency scenarios. And I'll show you the impact of the ECA/fuel mix scenarios first, and then afterwards the efficiency. If you move from 8 to 25% of LNG by 2050, it has a fairly modest impact on the overall emissions. If you have an efficiency increase of 40% over 2012 levels, you have one of the two top lines. But if you increase that either through additional policies or additional industry action to 60%, you make a significant dent in the emission growth. Although, and that's also a key finding of our report. Let me go back to this slide. In from a climate perspective, the most optimistic scenario is that after some growth, emissions will revert to their 2012 value by 2050. But that assumes a high share of LNG and low economic growth and significant efficiency improvements. Now this is a table for the other emissions. There's a couple of things that are worth bringing out here. When the share of LNG in the fuel mix growth, it also means that the CH4 emissions that have already been growing significantly over the last few years will grow even more. Depending on the scenario, by 2050 it will be 140 times their current, or 420 times their current emissions. Now those figures sound quite scary, but you have to imagine that it's from a very low base, and in CO2 equivalent terms, even in the high LNG scenario, CO2 remains the dominant greenhouse gas of that shipping emits. Most of the other emissions follow the CO2, with one notable exception, and that is sulfur, where because of the sulfur regulation, so the requirement that from 2020 onwards, as we modeled it, ships can only use sulfur of fuel with a sulfur content of 0.5%, or use a scrubber that has the equivalent effect. Sulfur emissions in absolute terms go down significantly, and even more in the ECA scenario than in the non-ECA scenario. And coupled with that, also PM emissions go down, but that's where we made a mistake in the calculations. And even though they go down or don't grow as fast here as the CO2, we have reason to believe now, but we have to redo the calculations that they might go down also in 2050. NOx also grows at a slower rate, much slower rate than CO2, due to increasing share of Tier 2 engines in the fleet, but it still increases over time. So to conclude this part, maritime emissions show an increase in fuel use and greenhouse gas emissions in the period up to 2050, despite significant regulatory and market-driven efficiency improvements. The main driver is the projected rise in demand for maritime transport, and especially unitized cargo. Efficiency improvements beyond business as usual can mitigate growth, but will not result in declining emissions. Sulfur emissions are projected to decrease significantly as a result of MARPOL Annex 6, and NOx emissions are projected to increase, although at a much reduced rate, also thanks to MARPOL Annex 6.
Thank you. So this is just the last slide. I just wanted to say thank you to you all for turning up this evening and for having a large amount of data thrown at you. And thank you again to the consortium members and all the people who were incredibly hardworking over that short period of time that we had to produce the work. If you'd like to see the study itself, it's not formally available, but if you Google MEPC 67/in.3, which is the title of the report as it's submitted to IMO, you will be able to find it on a couple of websites. We are also going to make sure we put it on our website, lowcarbonshipping.co.uk, and I'll put a version of these slides on for anyone who wants to use those afterwards. So can I just start by asking, does anyone have any clarification?
Yeah, it's not the various greenhouse gases you listed up. And it means that you had a doubling of HSC emissions. Could you elaborate a bit on that?
You got me off guard.
If you take up the last slide,
I can take, if you look at the growth in the unitized fleet, essentially the fleet that would be containerized, and you recognize that a portion of that fleet is refrigerated cargoes, that it would grow as well. And even in a situation where you look for mixes in the refrigerants such that they are growing, and I don't know the actual assumptions, but the upward trend there was very, very steep. A doubling could actually be related to divestiture of some of the HFCs but still have an increase in the density.
Yeah. So my comment would be that that might be an exaggeration because I think the substitutes will be before that. So I was a bit alarmed to see that number, but I think the reality is actually different.
I would also invite you to look at the HFC estimates for the current years, the historic years we studied, because if I recall right, we may have also been a little surprised that they hadn't been declining as much in the current period. Some of those are already should be on the decline, and we found evidence that they may not.
Any other clarifying comments? Yeah.
I always thought LNG was frozen upon voyage. How much of it boils up?
It varies depending on how long the voyage is and how much installation you have on the tank.
I'll give you an example. Cyprus to the UK, potential delivery route, because they've got LNG.
Like 5%?
Yeah? Okay.
We had a factor, I can maybe look it up in a study that we've done completely separately from here. And one of the default factors is less than, there's a certain percent of boil off per day.
Yeah.
And on a vessel, the expectation, it might be more along the 5% per boil, but when you look at what gets recovered, the net release is a very small fraction of the boil off as it gets consumed.
Any other clarifying questions? Yes, sorry.
In the pyramid, did you only consider LNG? Because there are apparently other fuels as well. You have styrene or hydrogen, so did you consider?
No, we had HFO, distillates and LNG. We kept it simple. We didn't look at the because after a literature review we concluded that there is literature that says that hydrogen has a potential. There is literature that says that nuclear propulsion has a potential, but it's all kind of speculative and also highly contested. So we try to stick with conventional wisdom at this moment, which was also confirmed by the stakeholders in the consortium. The alternative fuel next to liquid fossil fuels would be energy.
So there is a potential that the increase could be lower on CO2 emissions than the lowest, the 50% predicted, in combination with regulation, change of fleet performance, potential new areas, ICA areas, NOx areas, and as well new fuel mix.
Yeah, if you have more hydrogen in the fleet or more biofuels, then the emissions will be significantly lower. And,
Just to take into account of abatement potential factors provided by IMOs, I was going to ask you how much of that abatement potential you still include, or because better to ask how much do you leave out that could be applied at a reasonable price and what would do to your forecasts?
well, actually, the way we modeled it is that new ships entering into the fleet would first have to meet their EEDI, regardless of whether they apply energy or cost-effective methods to do so or non-cost-effective methods, because it's they have to. From the measures that are left then, after they implement those measures, certainly if you look at the fuel price projections of equipment where $100 most of the measures that are in the IMOREST macro are cost effective, except for solar and other. I mean, there's maybe 2 or 3 other measures in there that have both very limited potential and relatively high cost. So basically, in other words, we have exhausted all the potential of the measures that IMOREST surveyed
And you shoot the whole sheet.
because they, at some point in time, they were
But just follow up to Bill's question. How have you estimated the yield uptake of hybrid electric machinery on ships? Because they are most likely to be more energy efficient.
I don't think hydroelectric costs is in the IMOREST cost curve. And I know that there is quite a debate on whether they are or aren't more energy efficient. It also very much depends on where you're sailing, what kind of ship you're sailing. I think they are. They may have a benefit in terms of energy efficiency when you're doing coastal trades and short distances and a lot of maneuvering. Well, most of the emissions of the world fleet are on the large ocean-going ships, and if you're sailing at the ocean at a steady pace, there's very little advantage, I think, in having, as far as I understood the literature correctly, having diesel electric.
John?
Yeah, but you said a little bit, the importance of speed and associating with the speed today as can you say a little bit more about how you took that into account, specifically how you phased it out, and how sensitive that your choice of phase out was in terms of skills?
Did anyone at the back hear that question?
No.
Sorry, it was about, so the question was, in the scenarios for future CO2 emissions and other emissions, how was speed, which is currently at a sort of historic low, how is that assumed to change over the next 40 years? The answer is,
First of all, speed in our model cost is quite of a headache because it's kind of a central theme to the emission projections. It has links with fleet productivity, so the amount of transport work that you can provide per decade of capacity. It has clear links with energy efficiency, of course. And that makes it kind of hard to disentangle the different things. What we did is we assumed that, if I remember it correctly, the fleet productivity would revert back to its long-term average, and that about half of this was increased cargo load, and half of this was somewhat increased speed. But then we also assume that because of the high fuel prices, that freight rate, or that for a long time, I think even, I would have to look it up, sorry, I think even up to 2050, slow steam remains popular.
but if I could just add in response to that, so I think speed is really interesting, but it's also incredibly difficult. And what we've shown in the inventory analysis is that speed is very important for CO2 emissions. The next question that we'd really like to answer is what influences speed, which has been very difficult to do previously because it's been so aggregated. Now we've got it broken down on a fleet-by-fleet basis and in a time series which experience quite different market conditions. We can start to look at some of those relationships and maybe in the future produce scenarios that contain some of those relationships, but there just hasn't been the data until now to be able to come to that level of detailed analysis and evidence base to be able to think about speed in the future as much as maybe wanted to.
The projections, you had a wide range of alternative projections for scenarios, but can you comment on where that leaves us with the 2 degrees centigrade
Yeah, well, one first comment would be that shipping is currently at 2 to 3% of emissions. It may grow somewhat as a share of emissions, but in the end, it's the fossil fuel use in other sectors that is the more dominant factor in climate change and in the air resulting. The higher projections that I show are consistent with a world that goes towards a 6 to 8 degree increase in average temperature. The lowest is consistent with the 2 degree rule, and the other two are somewhat in between, so 3 to 4 degrees centigrade at the end of this century.
Would the lowest one then have to continue down in because the lowest one on the projection, the 2050, is roughly the same as the 12.
And that's assuming additional action on energy efficiency.
Yes.
Not necessarily. It wouldn't necessarily need to go down, because you can imagine that when, for example, the power and road transport sector decarbonize completely, that the share of maritime transport in the total emissions increases relative to its current level. So that even, you know,
so if I've understood what you're saying, then that would rely on other sectors cutting more.
Well, the question you ask is kind of difficult to answer, because it seems to have both a normative aspect, what should shipping do, and a positive aspect. So what do we think that shipping will do? And I'm answering here the positive question. And as to the normative question, if you think about, if shipping would have to reduce even more, or if we live in a world where climate change policy goes hand in hand with high economic growth, so shipping is still on one of the more on the higher line, and shipping would have to clear that. Then you come to what was previously mentioned, different types of fuels. Hydrogen, nuclear,
Like, maybe you can help us.
Maybe can I make a comment? I think in reply to your last question, I think that the question is actually quite clearly yes. So in any 2 degrees scenario, global emissions will have to go to nearly zero sometime in the second half of the century. And in all these shipping emission scenarios, there's no scenario where shipping emissions go anywhere near zero, if I'm correct. So therefore, I think the answer to your question is that in any 2 degree scenario, yes, other sectors wouldn't have to make bigger relative reductions than the shipping sector does according to these scenarios, even in the...
But why would we say that? Why should, shipping...
So I think we're segueing from the clarification questions into a discussion, which is great. I can suggest that we have 2 phases to this. The first one is in this room, and the next one then over a glass of wine. So why don't we have 5 or 10 minutes of discussion around the room, which can lean on anything, 5 minutes. And then those who want to discuss these points in a bit more detail, I can suggest we go afterwards. Jim, you want to say something?
No, go ahead. I'm just going to put up a graph that may be helpful when we get back to that. Well, I guess that since I'm doing it, I'll say it. There's some interesting evidence in the short term of a decoupling of growth in the economic recovery post-recession and a holding the line, at least in the near term, in shipping. That, we suggest, is due to a temporary set of conditions in the fleet that will eventually be reconciled, where slow steaming will recover to some degree of steaming at a speed that is optimal for those technology mixes, and other overcapacity will be taken out of the slack, the extra lower intensity, etc. But if you could keep this in some sort of a way, you still would need to insert some additional reductions just to get onto that lower curve. But what you're describing is some very important decoupling of what we perceive as economic activity and the amount of energy and work that we would be using carbon-based fuels to do. That problem is not unique to shipping. And the dialogue that you're beginning with is whether each sector needs to take the same quantity chunk commitment to meet that commitment, or whether they should take an equitable value of investment to meet that. And one of the things we're suggesting is that when you recognize that seaborne trade is tied more closely to the economy than some other growth, as you can see all along in here, the growth in CO2 emissions from shipping, and the earlier one with seaborne trade. Seaborne trade has been very tightly coupled with the economy. It started to decouple. That's a good sign for this discussion. It is not enough to get lower than the forecast. Is that enough of a launch into that part of it we need to? But I think that there's some help there.
Sorry, Nish, you trying to tell me something?
Yeah, I'm just trying to say that reception's on the basement, on the ground floor. So
Yeah.
we are on the lowest part of the building. We need to go to the basement, and we need to leave very soon.
We need to leave very soon.
And
So
continue.
that's at 8:30, right?
Yeah.
Okay. We get to this very soon. Julian?
Can I just say, I think this is such an improvement on the data that we've seen before. I think it's a magnificent study, and I'd like to congratulate you all on the results. It's totally realistic, and you know, when we have to struggle with these problems, how to solve it, we have to reduce CO2 emissions. It's getting outside the scope of traditional contracting within the shipping industry. So some really big investments have got to be made with different sources. That's a fact. And I think you've demonstrated so well today how complicated the system is. I love hearing all the different sectors. This is quite new and coming in very fine detail. And congratulations to you all, frankly. Thank you.
Thank you.
That wasn't a plant. Maybe that's a good point to break the wine. Unless there's any final questions that people would like to ask on this. Sure.
In relation to comparison against new reports, which are themselves successful degrees of uncertainty, presumably the comparison was also an indirect analysis on just how accurate the new reports were, or did they have a high degree of confidence before you began the comparison?
Okay, so in case anyone couldn't hear, that was a question about whether, when we were comparing against new reports, we were completely honest about the fact that there's also some uncertainty in the new report itself. Is that a fair representation?
Or at least you regard the comparison with modelled estimates as also an indirect query on the accuracy of the new reports.
Yeah, so it's an important point that we were comparing ourselves against a data source which is sometimes suggested to be slightly uncertain. I wouldn't go so far as to say I think that our AIS-derived estimates fuel consumption is more accurate on a per-ship basis, simply because we don't know the level of fouling, and we make quite gross assumptions about the impact of weather on the ship's fuel consumption. So I think the new report is uncertainty is of a lower order than our uncertainty, but it shows that it's still a very valuable comparison. Some of the scatter could be due to individual ship new report uncertainty, but certainly not the gross.
Without claiming that one's right, there are other lines on there that are showing the confidence bands on the FIT, and the confidence bands on the FIT, explicit in the report, as you can see, would suggest that both have errors that are overlapping and offsetting at least, and that there was a fair amount of confidence in the central message of a large number of new reports. Any single new report, we wouldn't have been able to make the claim that we could use it as validation. But that very large number, it was something you see in the context.
Right, on that I can see people are itching. Please join us for a glass of wine if you're still able to stay. Otherwise, thank you very much.